scientific article that proposes a new way to make unmanned aerial vehicles or UAVs fly smoothly and safely in complex environments with stable flight path. Modern path planning algorithms like A-star or RRT are excellent at finding a sequence of waypoints that get a drone from point A to point B without hitting anything. But the path connecting them is often a series of straight lines and sharp, abrupt turns. A real drone simply cannot fly like this. It can't make instantaneous, sharp turns. Trying to follow such a path would lead to instability, vast amount of energy, and put the vehicle under extreme mechanical stress. In search and rescue operations or urban inspections, where every second counts and stability is paramount, any loss of control or premature battery drain can turn a routine mission into a failure. Therefore, we have a second step, a method to take that raw, unflyable road and transform it into a smooth, dynamically feasible trajectory. The paper focuses on making that smoothing process better, leverages the mathematical power of cubic B-splines combined with adaptive optimization strategies. We built our solution on a powerful mathematical tool called B-Spline. B-splines are ideal for this task for three key reasons. First, they guarantee smooth velocity and acceleration, which means no sudden destabilizing jerks for the UAV. Second, they offer local control. This means if you need to adjust one part of the path, you can do so without causing large unpredictable changes to the rest of the trajectory. And third, the path always stays within a simple boundary. This makes it very easy to do a quick safety check. As long as the boundary doesn't hit anything, the path is safe. However, standard B-spline methods have a significant limitation. The shape and flexibility of the spline are determined by something called a node vector. Most conventional approaches use a simple, uniform distribution for these nodes. In practice, it can cause the spline to cut corners on sharp necessary maneuvers, or it can add needless complexity to long straight segments. The core insight of the paper is that to get the best possible path, that need to intelligently and adaptively place these nodes. To solve this, we designed a sophisticated two-stage optimization process, which you can see in this flowchart. The first stage is a global search. The goal here is to find the optimal structure or flexibility profile for the entire path. We use a genetic algorithm for this task. Think of it like a biological evolution. The algorithm creates a large population of different node vectors, each representing a different way to distribute flexibility along the path. It then tests each one against a fitness function, how good the resulting path. A fitter path is one that is shorter and has lower overall curvature and doesn't stray too far from the regional waypoints. The best solutions are then bred together, combining their good traits, and the process repeats for many generations. This powerful global search allows the system to discover a highly adapted node structure that is custom fit to the specific challenges of the trajectory, avoiding the trap of simple suboptimal solutions. However, a global search might still have some minor imperfections. That's where the second stage, local refinement, comes in. Once a genetic algorithm has found the best overall node structure, a more precise, targeted algorithm takes over. It's like a final quality control check. It scans the entire curve looking for any remaining hotspot, small segments where the curvature might still be too high for the UAV to handle safely. When it finds one, it performs a very localized adjustment to the nearby control point, smoothing out then specific segments without distributing the rest of the optimized path. This two-stage process is a central mechanism of our proposed method. It combines the broad exploratory power of a genetic algorithm to find a near-perfect global structure with the precision of a local search to fine-tune the final details. This ensures the final trajectory optimized for safely, efficiently, and dynamic feasibility. To closely emulate a realistic urban or suburban scenario, we constructed a 3D airspace measuring 2000 units by 2000 units with a vertical ceiling of 500 units. We designed this to be a realistic proxy for a mid-sized urban environment. It's not just an empty box. We populated it with obstacles of cylinders and cuboids. They effectively model the kinds of obstacles a UAV would encounter in the real world. Cylinders represent communication towers of support pillars, while cuboids simulate buildings or large containers. As we can see in the figure on the slide, these obstacles are placed to force any past planner to make non-trivial decisions about navigation and altitude changes. And then we compared the performance against three other approaches. First, the baseline polynomial. This is as a raw unsmoothed path from a standard planar. It is like a series of straight lines connecting main points. It is functional but often jagged and dynamically challenging for UAV. Second, the uniform B-Spline. This is a common simple smoothing technique where the B-spline nodes are spaced evenly. It's a basic but effective way to add smoothness. Um, the third, the classical B-spline. This is the step up using a short length parameterization to place nodes. This method is slightly more adaptive and it places more nodes in areas with tightened turns. And finally, our proposed enhanced adaptive B-spline, which uses a genetic algorithm for node placement and refines the path based on curvature. To measure success, we focused on four key metrics that are critical for real-world UAV mission. The first is path length. Shorter path lengths uh, means less flight time and lower energy consumption. Um, Maximum curvature. This is the most important metrics for flight stability. High curvature means sharp, aggressive turns which put stress on the airframe and can lead to instability. A lower maximum curvature means a smoother, safer, and more controllable flight. Computation time. This is the cost of the algorithm and determines its feasibility for near real-time replanning. And the straightness ratio. This tells us how efficient the path is. A value of 1 is a perfect straight line from start to finish. The closer to 1, the less the path had to deviate. As we can see, our approach consistently demonstrates a clear and substantial advantage across the most critical metrics. Our method has the highest computation time. It is the cost of running the genetic algorithm to find that optimal node placement. However, this is a very modest price to pay. For overhead, we are gaining a path that is demonstrably safer, more stable, and more efficient. For any mission where flight quality and energy conservation are paramount, like infrastructure inspection or search and rescue. This trade-off is not just acceptable, it's highly advantageous. So, to summarize our simulation findings, the results confirm that our adaptive approach isn't just a theoretical exercise. By intelligently placing nodes where the path is complex and finding the control points to respect curvature limits, we generate trajectories that are quantitatively superior. Thanks for your attention.